Okay, so I think we lose Frank briefly, but we get started now. So, good morning, everyone, or as appropriate to your time zone. Good day. Yeah, so as Frank said, this may not be a completely obvious title for kind of Monte Carlo based aspects of this school. And in fact, I think I've changed the title from what's on Indico, and that maybe gives you a clue why. I think the title on the Indico is to do with model independent measurements, and that's really what this is about. And it may also be surprising because in some cases, I mean, maybe this is not true, but when I was starting in the field, there was a deep suspicion amongst both experimentalists and theorists, actually, about the role of Monte Carlo, because it was often felt that if you had to use a Monte Carlo in a measurement, then that meant the measurement was model dependent, and that made it very hard to interpret in terms of the theory, and maybe made it very conditional. Maybe you were not really measuring things about nature. Maybe you were just tweaking Monte Carlo parameters. Now I rehearse that now just in case it's still in case that's still the impression people have in some areas, but I think that attitude is more or less gone. We're in a situation where the detectors are so complex that Monte Carlo simulation of the detector, as distinct from the event generator, is almost ubiquitous. Every major experiment has to do that. And also the state-of-the-art calculations, as you've been hearing in other lectures in this school, the state-of-the-art calculations are very often now implemented in what we would in the past just thought of as a Monte Carlo event generator, but in fact we're using Monte Carlo integration techniques all the time. We're very often coupling a state-of-the-art higher order calculation of electroweak or QCD physics with simulation of all the way through to the full final state, which then can be used in these detector simulations. So I think we've come a long way from the idea that using a Monte Carlo means is somehow suspicious in a measurement or in a theory interpretation. But what I want to do in these lectures is explicitly go through how an experiment can make use of a Monte Carlo without making their measurement dependent on the Monte Carlo, if you see what I mean. So we need the Monte Carlo to make the measurement, but the measurement in the end should not change if you suddenly change version of Monte Carlo, or if you'd use Sherpa instead of Pythia instead of Herwig, or whatever it might be. So the idea is that the Monte Carlos are tools to get to a result, but the result in the end is independent of the Monte Carlo and the model, and that therefore allows it to be maximally useful and maximally reinterpretable, and to also have a long shelf life, if you like, to live way beyond the value of the measurement should stand long beyond the value of any particular, or the currency of any particular Monte Carlo model. Okay, so let me see if I can actually, yeah, so good, the slides changed, that's good. So this is the kind of landscape in which we're talking about. I'm an experimentalist, and I'm approaching this very much from an experimentalist point of view, but I think the value of data for everyone as a scientist really doesn't depend whether you're a theorist or an experimentalist. The data is where we anchor ourselves in the end. It's in some sense the truth, in the sense that it's what's going on in nature. It takes a lot of resource to obtain it, particularly if you're talking about experiments on the scale of those at the Large Hadron Collider, but even a smaller scale experiment, there's a lot of effort goes into obtaining data, and a lot of work goes into it, and a lot of expense goes into it, and therefore it's unlikely, they're hard to reproduce for that reason. So that really, and yet it's awesome, as it says there, the data is really what drives the field forward in the end, and tells you whether your theory is along the right track, and tells you whether we're actually gaining understanding of nature. So all of that, the fact that data is important and hard to reproduce means that you should, when you produce data, you should make it you should try and make it stand, as I said, you should make it stand as a legacy of a given experiment that may never in the end in our field be repeated in exactly the same way. And you should not build into it theoretical assumptions. So that's really what this thing is about. And this is just reiterating that we want to avoid, as experimentalists, we want to avoid contaminating the data with irreversible dependence on theory models, because the theory models may change. That's the point of doing experiments, is to improve the theory models. We should publish the data in an optimally useful and reinterpretable way. So journal papers are great, but actually you don't want to have to read points off plots and things. You don't want to have to second guess what the experimentalists actually did. You like a very clear description of what you should do with this data and what and how it can be used. And we should try and distinguish clearly between our interpretation of the data and the measurement itself. So we may choose to interpret data in terms of, I don't know, standard model parameters, a W mass, a top mass, a parton density, whatever it may be that we're trying to target. There's absolutely, of course, it makes a lot of sense to target those things because because those are the language in which we're trying to understand nature. But we should try and say, okay, we've measured, for instance, let's go to an experiment in the previous generation. We've measured, for instance, the electron-proton deep inelastic scattering cross-section. That's the measurement. The interpretation of that is, now let's put that into a parton density fit and let's extract a gluon and quark distributions from the proton from that. Those gluon and quark distributions will depend on the theory sophistication. They'll depend on the order to which the calculations are done. They'll depend on whether you've included things like electroweak corrections inside them, whether you have a photon density, how have you treated the B mass and the charm mass in there. All of those things are interpretational issues which get you to the state-of-the-art QCD understanding. The measurement, which is electron-proton scattering, shouldn't depend on them all. And if the theory improves, then you should be able to use the same data in the new theory framework to extract a better parton density. And that kind of process, that separation of interpretation from the measurement, is really key to, if you remember anything from this talk, that's the thing to remember. That's what we're trying to achieve. And there isn't a single recipe. There isn't like, oh, here's the best way of doing it, and if you don't do it like this, you're completely wrong. The goal is the important thing, and depending on the measurement, depending on the experiment, there will be practicalities involved that mean we can get closer to that goal, or maybe we can't fully achieve that goal. But the point of the lecture really is to make that goal explicit and raise some issues that have to be discussed in order to try and get there, in order to try and make yourself make your measurement maximally useful and interpretable. A corollary of this, which ties this lecture also to the Monte Carlo and theory parts of this school, really, is that if the experiment is going to go to all these lengths to measure real stuff in a model independent way, the theory needs to actually predict real stuff in a model independent way. So a super higher order calculation of Higgs production, for instance, is useful, but it's of limited use if it's not in a form that you can actually impose the experimental cuts on the phase space cuts on it, for instance. So if you're measuring the Higgs and you're measuring it in the Higgs to gamma gamma, there's no point having a very, very high order, almost no point, having a very, very high order calculation of Higgs production if it doesn't include a simulation and a calculation of the Higgs decay to 2 photons, and if it doesn't actually allow you to impose acceptance cuts on that. So the detector will not measure all photons. It will require them to have a certain rapidity range and a certain PT range, for instance. And if you can't impose those things on the theory calculation, then you're going to have to use some way of, you'll have to introduce them because the experiment enforces them, and that introducing of them will introduce theoretical model independencies, which are probably at a less precise than the calculation itself. So the corollary of experimentalists going to all the effort to make a reusable and reinterpretable measurement is that the theory needs to also be able to predict those things, and that's where we start gaining our knowledge. So an overview of these two lectures then is I'll spend some time discussing what we actually measure, and I'll talk about how Monte Carlo generators, event generators in particular, are typically used in those measurements. I'll then talk about detector effects on various particles and what we mean by that, and then mostly in the second lecture tomorrow, we'll get on to then putting those ideas together to make into how we make measurements as useful and model independent as possible, how we correct for detector effects, the concept of a fiducial phase space, what we mean by final state particles. Hello, can you hear me okay? I got some background noise. Was that someone trying to ask a question or? No, okay, I'll carry on. Oops, sorry. So the concept of a fiducial phase space, what we mean by final state particles, and it's a surprisingly complex issue sometimes. and issues of things, then kind of higher order issues, if you like background subtraction or not. And finally, I'll finish with some, a lot of this is gauged around measurements of, quote, standard model type processes, but I will also talk a little bit about the implications for looking for physics beyond the standard model. The lecture's sort of focused on the Large Hadron Collider with a bias towards ATLAS, really, because that's where I come from, but that's not because but the principles are applicable elsewhere. So I hope that doesn't put those of you on different experiments off too much. Okay, so what do we actually measure? In the end, if you're going to be absolutely purist about this, we measure electronic signals in our detectors due to interactions with traversing particles, and those particles are producing the collisions. And these signals from multiple subdetectors, so by which I mean things like the tracking detector or the calorimeter and stuff, the muon chambers, typically, they're combined in a time window, so you know which ones are associated with a given beam crossing, to make a collision event, and that event is reconstructed to give you, in the end, a list of identified particles and jets along with their kinematics. So there's a Feynman diagram here of some interesting process, triple gauge vertex at the LHC. This might be something we're trying to measure, but in the end, what we see is the electrons and the muons that you see emerging there, and the quarks we will not see. We'll see hadrons produced from quark fragmentation. So I'll go through in more detail how we extract the information that we want from this. So the things that give us those electronic signals in our detectors, and here's an example of a detector, and as I said, biased towards ATLAS. This is ATLAS, but it could just as well be a generic particle detector. It could even be a neutrino detector in an accelerator neutrino experiment, for example, or a cosmic ray detector. Either way, what we see is or a flavor factory detector, of course. There's nothing special about this. It could be LHCb or Bell. But in all these cases, we, of course, those electronic signals, we only see final state particles. So electrons are stable. So it depends, what we mean by final state is do they live long enough to actually impinge on our detectors? So electrons certainly do. Muons do. Of course, muons are not actually stable. They have a lifetime. So typically that means that a 20 GeV muon will decay after about a kilometer or 1.2 kilometers. So they're certainly stable enough to reach our muon chambers. Typically, you see this filled in the box there. You can obviously calculate the distance traveled, average, and the lifetime, and it's done there for the muon. That's an important set of parameters, and typically an experiment will make some more or less arbitrary cut and say that any particle with a lifetime longer than something which is typically 10 picoseconds is considered stable, and any particle shorter than that is considered unstable, for the purposes of what are we measuring. So do we consider we're measuring, if we consider we're measuring the final state, then you would not include a particle with a lifetime shorter than 10 picoseconds in the final state, but you would include its decay products instead. So taus are somewhere in that. They have a tau 0 of 0.3 picoseconds. They will decay therefore after about a millimeter for a 20 GeV tau. You see measurements where the actual tau is reconstructed, because we can tag that 1 millimeter is far enough that we can observe the decay vertex. So under certain assumptions, you can reconstruct the tau completely. Of course, the tau decay will involve a neutrino, so there are complications in that because the neutrino will not be visible. But again, this is one of those gray areas where in some measurements it may be useful to just measure the tau decay products and maybe tag the tau, maybe tag them as coming from a tau, but not reconstruct the full kinematics. In other cases, it may be better to add a few extra assumptions in and actually reconstruct the full tau kinematics. Kind of depends on the measurement. Neutrinos, I've already mentioned, and neutrinos are stable, that's fine, but they're invisible, which is not so fine. So again, in some circumstances, I mean, what we in the end measure is missing energy. In some circumstances, that has a very good correlation with a neutrino if there was only one neutrino in the event, but that's an assumption. And if you have more than one neutrino, or if you have other invisible particles, maybe beyond the standard model invisible particles, the labeling of missing energy unambiguously as a neutrino may not be possible. Quarks and gluons, of course, they're confined, so we do not measure quarks and gluons. We do measure the hadrons they produce. Some of those will be considered stable, some of them will be considered unstable. If they're considered unstable or stable, in the end, we can, the general way of reconstructing quarks and gluons, in a sense, is to apply some clustering algorithms. So you see a jet formed from them. That's not a unique definition, so you need to be very clear that the jet algorithm is actually defining the jet. It's not that there's a jet that has some existence independent of the algorithm. You have to specify the algorithm, and then you have to use the equivalent algorithm in the measurement and in the theory if you want to be able to compare like with like. Of course, also unstable hadrons, depending on the measurement. If you're measuring rare decays, for instance, or flavor physics, then you probably care that they decay to leptons, photons, other stable hadrons. And also even if you're not trying to measure the details of the decay, the fact that you get electrons and muons from charm and bottom hadron decays, for instance, is something you have to make decisions about as to whether you treat that as a muon or whether you treat it as a hadron, for instance, in whatever measurement you're doing. In general, I hope you get the idea that I'm not giving you a prescription on how to do this. I'm really trying to raise the idea that you have to answer these questions about any measurement, because if you want a theory, if you want to use that measurement in the long term, you need to know what choices were made in that measurement. And some of these choices in some circumstances will be better than others. Sometimes they will make the measurement more model independent. Sometimes they will introduce theory assumptions. You may make the judgment that the price of paying some small model introducing some model dependence is worth it because you get big benefits in other ways, for instance, in precision under those assumptions. And that's a choice you have to make when you're designing a measurement. But the main point of this discussion is to say, you have to make those choices and be aware that you're making them, because very often you find that they're implicit in a measurement, and it's very hard to work out afterwards what was actually done. Final one on there, of course, is photons, and they're stable, and we can measure those. Okay, so that's the kind of situation we have to play with. Oh yeah, finally, sorry, that you often see measurements that claim to be measurements of WZ, Higgs, top. They're unstable. They're clearly not final state particles. They're in general not uniquely defined. Now, of course, you can make a measurement that will be sensitive to the W mass or the Z production cross-section or the Higgs cross-section or whatever. I'm not saying that those measurements are invalid, but if you drill down into a good paper that says we measured the top cross-section, for instance, it will have to address all of those issues above, because in reconstructing, the top is a great example because it involves everything. If you have a top, it will generally decay to a W and a B jet. So you have to make decisions about the B and the jet finder and how you tag the B, and whether you treat the B's final decay products as stable or whether you treat the B as stable. The W that's produced then will, of course, immediately decay. Usually we will tag the leptonic decays. So it may decay to a tau, in which case you have to decay those. You have to make choices about how you treat taus. More often we will look for the muon or electron decays because they're somewhat simpler, but even there you have to make choices about how you identify the missing energy, because there's a neutrino produced as well. Are you going to assume that that's a neutrino? Are you going to produce the measurement defined in terms of missing energy? So I'm not saying that we can't measure WZ, Higgs, and top. I'm saying that they actually, that in a sense well, actually, in a sense, I am saying we can't measure them. They're not part of the final state. So that whatever you do about them will be at some level model dependent. But if you say, I have an operational definition of a top, which means something with an electron and missing energy and a B-tag jet in this kinematic region, then that you can design those cuts so that you're very sensitive to top in the standard model, and you can measure it that way. And again, there's no unique recipe for doing the best measurement. You have to consider the measurement, but you do have to answer these questions. And it's certainly not good enough to just say, I've measured W or I've measured top. You have to specify how you defined the W or the top in terms of its final state decay products. So this is the kind of example of what's going on in a detector. For those of you who are experimentalists, this kind of picture will be very familiar. But if you're thinking about what happens to the particles I produce from my matrix element or my simulation in my final state event generator, This is what happens to them in a detector. So either in a real detector or in the simulated detector, and I'll come on to say a little bit about detector simulation shortly. But you see that this is how we distinguish what they are. So we have going kind of clockwise from my left, the muon, which will penetrate all the way through the detector and register in the, it's a charged particle, so it will give a track. It will register in the inner tracker and in the muon spectrometer on the outside. It will probably also do small amounts of energy throughout the calorimeter, but it will not stop there. The photon will leave no track, but will leave an energy deposit in the electromagnetic calorimeter. It will shower early. Protons and other stable hadrons charged hadrons will leave a track and then will penetrate deeper into the calorimeter. So, but we'll stop there. And you see there in the hadronic calorimeter. We have neutral hadrons like the neutron, which will also travel far enough to leave an energy deposit in that hadronic calorimeter, but will have no track on the way. And therefore, of course, will not bend in the magnetic field. Typically, there's a solenoidal magnetic field here. Electrons will leave a track and will look like a photon, except that there's that track there as well. And then neutrino will do nothing. So the only way of guessing there was a neutrino there is to look for an energy transverse momentum imbalance in general. Okay, so the kinematics of these identified particles are reconstructed and the information about the event can then be inferred. But those measurements are not exact, of course. We don't build perfect detectors, we try, but we can't. There will be some stochastic effects in the calorimeter, for instance, depending on, even if you had so-called perfect calorimeter, perfectly calibrated, there's still a stochastic effect in the way that the particle will shower in the calorimeter. So there's an inherent statistical spread on the results there. Likewise, you know, there'll be experimental resolution on the precision of the points in the tracker, and there will also be some finite knowledge of the magnetic field. So there's all of these things add up to an experimental resolution. So the picture of nature that we're building up that you see down there will be blurred by these effects at some level. So how do Monte Carlo event generators enter into all of this? We use them to simulate the collision events based on some underlying theory, which is usually the standard model, but may also be an idea about a beyond the standard model. And we then we combine, so that there's some kind of hard process that can be predicted there. And typically that has to be combined with phenomenological models, which have parameters tuned to experimental data. This is usually for non-perturbative effects from QCD. So to some extent, the parton densities in the proton enter in here, but although they are to a very large extent fixed by other measurements and by perturbative QCD now. for a wide range of input values anyway. But still, the way quarks and gluons turn into hadrons, for instance, or the way the other bits of the proton interact with each other, or if you're in a heavy ion collision, of course, the bulk effects of the nucleon-nucleon collisions accompanying the hard process, all of those things have some range of theoretical insight into them, but also some range of phenomenological modeling and some range of input data that they're tuned to. What the generator is giving you here, you see a list of numbers. You know, this is the HepMC event format, which is more or less ubiquitous now. Actually, HepMC3 would have been a more up-to-date version to put on here, but you see that you'll have a list of vertices, you'll have a list of the incoming particles to the vertex, a list of the outgoing particles to the vertex and their form momenta, and so on. And the graphical representation there from Chirpa is shown on the right. So you see there that there's a lot going on. There's a hard process here, but then there's also what happens to the rest of the proton. There's the QCD radiation and electroweak radiation from the particles emitted from the matrix element. There's a stage where they turn into hadrons, and then there's a stage where those hadrons decay as well, sometimes initiating new showers and new radiation. And this is the kind of event record that you'll get. And these are only part. The thing to mention here really is we're not looking at a picture of nature here. Okay, very often there's not really physical reality to these vertices, and you would hope not, because it's so complicated, complex as well. What this is a calculational tool. It's a way of getting from the physics, what we think is the short distance physics, and implementing it in the calculation, and in the end producing a prediction for the final state. And there can be several equally valid ways of going from the Lagrangian to the final state particles. And those intermediate steps are not guaranteed to be the same in any given generator. Doesn't mean the generators are wrong. It just means that they may have taken a different calculational approach. But something like a propagator in this diagram or something, it's a tool to get to the prediction. It's not a prediction itself. Okay. Obviously, in the end, what propagators you use, I think, for example, they're gauge dependent. So we have to be careful when we're as an experimentalist. This can look a bit baffling and say, I want to measure something from this thing. Well, don't just measure the final state. Don't try and measure some intermediate step, because it's not really physically meaningful, to be honest, and it's not unambiguous. So which bits of this tree are safe? And that's really what I was talking about. That's why I went through this describing what final state particles are, because whatever cool calculational tricks different Monte Carlo generators may use to get from the Lagrangian to the final state, they should all agree on what an electron is, or what a muon is, or what a pion is. So if we stick to measuring those, then we know we're doing something at least relatively model independent. The other way so that's, in a way, I guess that's a kind of warning of how not to use Monte Carlos. Don't use a Monte Carlo to try and drill down and find the true Z or the true W or Higgs in the event record, because it's not guaranteed to be model independent. What we do need to use Monte Carlos for is as input to our detector simulation. So we basically always have to simulate the effects of our detectors. Typically, this is a software model of a complex detector that is written usually in Géant 4 these days, which is a software library that includes the known physics of interactions between particles and material. It's used actually beyond high energy physics. It's used in other applications, medical and engineering applications as well, to simulate these things, although it comes from high energy physics. So Atlas, CMS, and LHCb and Alice have a simulation, a software model of their detector, which includes things like the beam pipe. It includes the magnetic fields. It includes the material, the dead material, the density, the service pipes, the cooling system, which particles can scatter from, and things like that. It's a very, very detailed model. And the generated particles pass through this model step by step through the material, and they interact with it, and the magnetic field, where they also interact and radiate. And at each step, this is a Monte Carlo process. So at each step, there'll be a random number, pseudo-random number generated to say, well, in this step, how did the particle move? Did it Bremsstrahlung here? Did it in the magnetic field? Did it interact with the nucleus in this silicon that it's passing through? Did it generate a hit in the detector? Did it shower in the calorimeter? At each step, and you can obviously set the granularity of those steps to optimize the simulation and not waste too much CPU while still getting reasonable results. There's a whole art to this. You can tune them on test beams and so on. But that's a really key important. That's the next step after the Monte Carlo event generator hands over. It will go into one of these software models. There's also then a digitization step. So typically we have on detector electronics, which even if the detector would have given you a kind of very precise continuous signal of the energy of a particle, that's then passed through a digitization step, which may have a finite what's the word? Oh dear. The response range of the dynamic range. You may have a finite dynamic range with some number of bins where you have, with an overflow bin or something, and you have to, and may truncate the energies at some level. All of that stuff has to be done. And the idea is after you've done that, then the data is indistinguishable from real data in terms of its format, at least. So then you can take the same reconstruction code that you use for the real data from the experiment and apply it to the simulated events. And that reconstruction code typically will be identical depending on whether the event that you're reconstructing, and by reconstructing I mean trying to identify tracks and electrons and energy deposits and so on. The reconstruction code won't care whether these data came from a simulation or whether it came from the real detector. So all that part is specific to an experiment. It's a very detailed, specific model. It may even be specific to, it probably will be, specific to a given year of an experiment, because typically over Christmas or something, you'll go in and change some things, and then you have to change those things in your software model as well. That detector simulation is very CPU intensive. It's typically done on the worldwide computing grid. The codes, actually, it says they're often not publicly available. I think actually most of them are now. In principle, you can go and read the Atlas GitLab repository for its full simulation, but they're still not really publicly usable, partly because of the CPU, but also because they're just so complex that to configure them correctly, it's not something your average theorist or your average member of the public or your average experimentalist from a different experiment will want to do. So it's not that they're secret, it's just that they're very complex, and so they're not something that you will 20 years after the experiment is done just go and fire up and rerun probably. And they will also, and part of the reason for that also is that they are, as I mentioned, they're time dependent, they're condition dependent. They will also include accelerator specifics. So, in 1 year, the LHC runs with a certain amount of pileup and beam backgrounds, in another year with a different lot. And somehow the detector simulation also will fold in the beam conditions and things. So that becomes really complex to check that you're actually doing it okay, to check that the detector calibration is done correctly for that particular condition. But so that's all kind of experimental work, but the necessary input for that is the Monte Carlo event generators. So the generated events are used to compare measured data to the expectations from a given theory, a standard model prediction or something else. Usually we're just asking, does the data agree with this theory or not? They often use to subtract background processes from the data. This can include kind of beam backgrounds and things, or non-beam backgrounds, cosmic rays, but it also can include background processes in the collisions themselves. That's now already getting into the gray area. Sometimes that's a good idea, sometimes it's not. And I'll come back to why later in these lectures. And it will be used, which is what I will focus on for the rest of this lecture today, to correct for detector effects by comparing the truth level Monte Carlo prediction with a reconstructed level Monte Carlo prediction. So more on that, I think, straight after this. And another actual important application of Monte Carlo event generators, which I won't discuss further here, but it's very much worth bearing in mind given the activities around the community now, is that this is a really powerful tool for planning the sensitivity of future measurements and folding in some semi-realistic aspirational detector design with some resolution and things, and seeing what the performance of the detector needs to be in order to achieve the sensitivity or the precision that you want with your eventual measurement. So all of those things are kind of very deeply integrated into the way we do particle physics experiments now. And I'll talk in particular about the third one now, but this is the kind of the chain that we're talking about. So simulation and experiment, you have a Monte Carlo event generator there on the left. It gives you a list of stable final state particle 4 vectors. You pass that to the detector and trigger simulation that you have in your software model in Xeon. That gives you this digitized readout, and then you pass that to your event reconstruction and you have the data for analysis. And in the experiment, that looks like this, where you have the actual collider, you have the actual particles, they hit the actual detector and its trigger, gives you the digitized readout, and from that point on, everything else is the same. The event reconstruction and the data look the same. So what do theorists want to do with our data? We and theorists, physicists in general, what do we want to do with our data? Usually we're asking how well does the data agree with the prediction. Often the prediction often comes as a set of final state truth particles from a Monte Carlo event generator. It won't always, but that's the most model independent. Well, that's the place at which you can make the most model independent comparison, and I'll come back again to that later. So we have data corrected for backgrounds and or detector effects using a Monte Carlo simulation, and we have standard model Monte Carlo predictions tuned or validated with the data. We have to be really careful here because we don't want the data to depend on the prediction we're constraining. The Monte Carlo appears in both those boxes, and if you're not careful, this can become a completely circular loop and you're not really learning anything new from the data. So the care that needs to be taken on the experimental side is to avoid the dependence of the measurement should not depend on the prediction, basically. And if we're looking at also, we have many predictions, maybe beyond the standard model predictions we want to test. They're compared to usually uncorrected data from the standard model Monte Carlo, often constrained by data, and the parameter and bits of parameter space will be excluded. That has somewhat slightly different use cases imposed on the data, on the measurement, on the data. Ideally, we want the data to be reinterpretable under many beyond the standard model models. We don't, there are so many ideas out there that we don't want to have to do a dedicated search for each of them. We'd like to make some fairly, we'd like to make searches for one or two, but be able to reinterpret them in the shape of sensitivities to different models that are kind of maybe related or looking at similar final states. And again, we also don't want to tune our Monte Carlo such that actually we may be tuning away the sensitivity to beyond the standard model physics. We want to take the standard model prediction seriously, and if we start tuning things such that it's inconsistent with the standard model in the end, then we need to be aware of that, because again, otherwise we will never see anything new. We'll only see what we expect, because we'll assume everything else is tunable can be tuned away. So the experimentalist's job really in doing this is to measure interesting things that can easily and reliably be compared to a theoretical prediction. That's I guess summarizes the previous discussion, and I hope I've given you a flavor that isn't maybe completely obvious and simple every time. I'll just advertise Rivet here, which you'll see in the tutorials, and which is quite a widely used tool that's very relevant for this at the moment. The idea of Rivet is it's a library of preserved measurements, where those measurements are preserved in terms of what was the final state that's measured. And so as such, it can then be used to validate different Monte Carlo event generators, because it's focusing only on the final state. So any Monte Carlo event generator should agree on the final state, even if the intermediate steps don't agree or use different assumptions. Experimental results can be that Rivet uses come from HEP data, which is the kind of standard repository for digitized published measurements. You write an analysis routine that selects events and plots the relevant variables based on the final state particles that can be compared to the data from HEP data. It makes sure, if you're a theorist, a third-party person using someone else's measurement, it makes sure that you're making the correct selection cuts when comparing to the data. We have a large number of analyses in there, and it saves you recoding all that up yourself and possibly making errors in the process. It's already been very heavily used for Monte Carlo generator development and validation and tuning, and is now being increasingly used for testing BSM physics as well. So those of you who are experimentalists, when you publish a result, please make sure you provide a Rivet routine too. Maybe also worth adding to, if you're a Monte Carlo generator author, a theorist, then actually, if you make a prediction for a calculation that's a measurement that's preserved in Rivet, where it's on the HEP data plan, that those could also be preserved in HEP data, because they're often very time consuming and difficult to do as well. So it would be very nice in future, and this is the hope in future, to build up a library of state-of-the-art calculations for each of these analyses as well, which is something we can discuss afterwards if you like. Okay, so I said I would spend the rest of this lecture talking about detector effects and how we correct for them then. So that whole business of Rivet and HEP data, the idea is that the Rivet analyses there are in terms of final state particles, not in terms of the electronic signals from the detector. So that implies that we've intervened, that we've done some correction. And that's what we mean by detector effects, basically. So the efficiencies you'll hear talked about, there's a non-zero probability that some particle, even if it passes through the detector, it may not be reconstructed. Either it will go in some crack where we have no sensitivity, no active detector, or just stochastically it will fluctuate so that the energy appears to be much lower than it really is, and therefore it will fail the cuts, for instance. There's also effect backgrounds. There's a non-zero probability that a particle will be reconstructed even though it wasn't actually there, or you can misidentify a particle. So you could have a spark in the calorimeter which looks like a photon, for example, but also you could have, for instance, an electron that for some, just as a statistical tail, doesn't actually shower as quickly as electrons usually do, and actually punches through into the hadronic calorimeter, and therefore is either not correctly identified as an electron, or actually looks like an electron with some hadrons as well, even though there was only an electron. And then even if you measured the particle properly, you won't get an exact answer for its energy or momentum and angle. There will be some smearing on that. There'll be some resolution effect there. So we need to understand these effects. We need to know what our detector is doing, and we need to account for it. And in some cases, we can reverse it. You can't remove, obviously, stochastic effects completely, but you can say that I have a confidence that the real particle's energy was within this range to some extent, with some associated systematic uncertainty, and then that can be used to compare to the truth level. So, for example, muons here, and the momentum of a muon will be measured in the inner detector and the muon spectrometers from the charged particle track, usually with some isolation requirement imposed, which has implications for whether an isolation requirement may not be the right thing if your muon came from a charm decay, and that's actually what you want to measure, because it may be surrounded by hadrons. But for a muon from a W boson decay, for instance, it's probably a good thing to do. You can calibrate that. We know we have some reliable sources of muons, the Z boson and the J psi, both decay to mu plus mu minus some fraction of the time. We know their masses are very precisely measured elsewhere, and you see two examples from Atlas here of the peak of on the left a J psi mass from relatively low energy muons, and on the right the Z boson mass. And the data, the detector level data here are the black points, including all the smearing from the real detector, and in the case of the Monte Carlo, all the smearing from the J1 simulation. And you see the uncertainties associated with that, and you see the level of agreement achieved. And you'll see that there's the red line says Monte Carlo, and the dotted line says Monte Carlo uncorrected. What that means is that our best guess of the detector, our best guess of this resolution from the detector simulation from J1 is the dotted line. And then you say, okay, how well does that do? Well, it does pretty well, but we can do better than that because we have the Z and the J psi, and we know what their masses are and their widths are. So then you apply ad hoc corrections to the Monte Carlo after the fact to get better agreement and improve the resolution and improve your ability to correct for these detector effects. So the software model on itself is never perfect, but it does. The idea is to put everything you know about your detector from test beam and from surveys and so on in there. Hope that you get somewhere pretty close, and that's the dashed line, and it is pretty close. But then you can also do an in situ calibration with what you know from the actual measurements in the experiment itself, and improve that. And you'll see that in a few of these plots. This is the efficiency of the muons, for example, here as a function of pseudo rapidity. You see that Atlas has actually a drop in efficiency in the central region, and that's because there are various cooling and signal cabling basically coming in and out of the detector at that point. So we lose something like 15% of our efficiency at rapidities around in the central region at 90 degrees. But it's pretty high and constant other than that, and even there it's still 85%. And on the right there you see the momentum resolution as a function of as a function of the true momentum, as obviously taken from the simulation in that case. So on the left you have the actual measured efficiency using things like Z decays and the simulated efficiency, and you see that actually that is really well understood. Although we have that drop in efficiency, we've modeled it well in our detectors, so at some level it doesn't really matter. It loses us some events, but we know exactly how many events we've lost. Electrons and photons, again, similar kinds of plots. There's a plot there on the right, which is the Z peak calibration for an electron as well. The efficiency curves there again, and showing the most for different levels of selection. So this loose, medium, tight, you'll hear discussed often by experimentalists. There are different levels of moving around the ROC curve, if you like. So how many fake electrons will you, if you have a loose cut, you'll have a higher efficiency, but you'll have more fake electrons coming from things like pi zeros and so on. So Okay, that's the electron. And again, the main thing about this is, first of all, to build your detector as well as you can, so the efficiencies are high and the resolutions are high. But then, almost more importantly, is to understand that properly and model it well in your detector simulation. Jets, as I said, these partons lead to a high momentum scattered parton will lead to a collimated set of hadrons, which we form into jets. We build them with jet algorithms, usually the anti-KT algorithm, from calorimeter clusters or tracks or some combination, energy flow combination of the two. We will calibrate them by balancing them in general with other calibrated objects, with electrons, muons, photons that you've just seen, or balancing jets in different regions of the detector. And you see here that from 2018, the Atlas state of the art there. Taus, we can reconstruct them with different efficiencies depending on what they decay to. There is a finite range of possible tau decays, and you see them listed there. The key thing, I guess, really is that there's always a neutrino involved. These are the hadronic decays. There are also charged leptons can be involved in these decays too. But again, we have no control over how the tau will decay, but we can, stochastically or statistically, we can simulate it and understand our efficiency for that. These are the hadronic decays of the taus, and again, some more examples here of how the visible mass of a di-tau pair is reconstructed, and the true energy of a tau is reconstructed. Neutrinos are the only completely invisible particle in the standard model, but of course, a big part of what we're doing is looking for things beyond it, in particular, in this case, dark matter, which would also be an invisible particle. And really what we're doing there is reconstructing the energy momentum imbalance, in the transverse region. Remember that for a proton hadron collider, we don't really have control over the longitudinal momentum, because we don't know what the momentum fraction, a priori, we don't know what the momentum fraction entering into the hard process was. So in general, the hard process is boosted by an unknown amount along the beam line, and we lose an unknown amount of energy down the beam pipe. So we can't do the Z component, we can't do missing energy there, missing momentum there, but we can in the transverse region. So if we have a huge jet and it's not balanced by anything, the natural assumption would be that that's a particle we couldn't measure, probably a neutrino. But of course, in a monojet search, you would say, well, what if it was a dark matter particle, and compare to the predictions of the standard model there, and to see whether there are any signs of an excess. And that involves, it's an absence of momentum. That implies you have to make choices about every other bit of momentum you measure. So what you see on the top of that equation there is the missing energy is the negative of everything else. So it's the electrons reconstructed as well as you can, the photons reconstructed as well as you can, the taus reconstructed as well as you can, possibly with some way of trying to treat the fact that there's a neutrino in the tau decay. The muons that are reconstructed as well as you can, the jets, and then anything that's left over that wasn't energetic to go into a jet or anything will still potentially have an impact on the missing energy. So it's actually sounds like a kind of simple object maybe to reconstruct. It's the most complex object, because it implies doing everything else and then taking the minus, so the negative of it. So final topic is for today is just to say we often want to present the data corrected for the detector effect so we can compare to the final state truth level particles, because people don't have access to these full things. So to look what we mean by that, this is a measurement from the early days of Atlas. It's a run one top anti-top cross-section paper, and it's the transverse, the HT, which is a transverse mass distribution at a reconstructed level. And you see there's a Monte Carlo simulation plotted on there, the data points in black. That measurement can't be compared to anything other than the prediction in the paper, because it's a completely detector level measurement. So in order to take a new calculation of TT bar physics and compare to these data, you'd have to push it through the whole of the Atlas simulation and make sure you'd applied all the detector level cuts the same way. that we've done in the experiment. So the way we can make that more friendly as experimentalists is to do the full correction. So here you see not only that it's this detector level, but there are also backgrounds in there as well. We can correct for backgrounds from fake particles and sometimes those from similar final states. And I'll come back to that towards the end of the lecture tomorrow. But more importantly here is we can correct for detector inefficiencies and scales and unfold resolution effects. And this is what you see on the right there is a migration matrix with the true this is actually not for the top, this is for a 4-lepton final state. But you see the true 4-lepton, the particle mass, the mass of the 4-lepton system here, using the true particles from the Monte Carlo event generator on the horizontal axis, and on the vertical axis, the 4-lepton mass that's reconstructed from the detector after all those calibrations. And this is a migration matrix there, which is where the fact that it's not all along the diagonal is due to the finite resolution of the detector. But we know that we've got a good handle on it. If we trust this matrix, we can essentially invert this matrix using various different techniques, and therefore produce something which is within some uncertainty the true 4-lepton mass, and that can then be compared to a calculation of the true 4-lepton mass. So it's this correction and evaluating that migration matrix clearly needs a Monte Carlo event generator. That's the only way you have a handle on the truth momentum distribution. We have to be careful as the corrections can depend on the underlying physics modeling. So we have to deal with bin migrations, which depend on the underlying distribution. And so there's a whole, and efficiency corrections depending on the kinematics. So there's a whole industry of validating and checking and doing this unfolding in a controlled way. And of course, you can also use a different Monte Carlo event generator to do it, and you should get the same result. And if you have a big systematic, which is, I did my unfolding with Sherpa versus my unfolding with Pythia and Maggraph, for instance, A versus B, then that's a 2-point difference. If that's a big difference, then you would really worry, because what if you had a third generator? It might be different again. You don't really control that error very well. So just to finish up, looking at the simulation and experiment issue, this is the chain that I showed you before, where we start with the Monte Carlo event generator and we go through to our data for analysis. And this is what that looks like in the actual experiment, where we end up at the same place. And the point of once you have this chain is that with that simulation and experiment chain, you can actually make the mapping between the Monte Carlo event generator on the left and the data from on the right. That is essentially that migration matrix that I showed you. And you can invert it, which is that red arrow there, and you can change all the parameters of that chain and see how reliable that inversion really is, and use that to evaluate the uncertainties. And then you can apply that red arrow to the real data, and you think that within those uncertainties, then you've actually measured the true particles that were produced in the collision. Obviously within some uncertainty, but in a controlled way with a controlled uncertainty. I have one more topic I was going to cover today, but I think maybe it's better to stop now and I'll pick this up tomorrow, because that's really a good place to finish. That's what we mean by correcting for detector effects. The next topic would be dealing with what I call acceptance, but I will come back to that, I think, tomorrow morning. So are there any questions now? I'm sorry, I used up most of the time, but if there are questions now, I'm happy to take some.
Thanks a lot first, John, for this nice lecture. I don't see any questions yet in the chat, but everyone who wants to ask a question, feel free to raise your hand or speak directly. Ah, there's a question.
Yeah. It's a reader migration matrix, yeah. So I maybe went over this a little quickly, but if we look at this slide, I hope you can see the slide now, probably not full screen, but I think that's okay. So what that is it's that full chain of that I showed you here, this chain that you can only make it for the simulation. So that full chain there, where we have the particle 4 vectors on the left and the data for analysis, the reconstructed data on the right. For the example of the migration matrix that I'm showing you, those particle 4 vectors are the true 4 vectors of 4 leptons. So let's say 4 muons that have been simulated from a Monte Carlo event generator. and they're what would be input to the detector simulation. So there's no detector involved. They're just what comes straight out of the Monte Carlo event generator. And on the right, the data for analysis would be what we think after all the simulation, how well have we managed to reconstruct those muons, okay? So same 4 muons, the absolute true 4 vectors on the left, what emerged from our detector simulation on the right, and then we plot them on the migration matrix. This horizontal axis is the truth from the Monte Carlo generator, the Monte Carlo event generator, and this vertical axis is what emerged from our detector simulation and reconstruction after all that work. And we're looking at the migration between the two. And the migration between the two is essentially what are the imperfections of our detector? How well did it do? If a muon had 20 GeV of energy, it will come out as hopefully 20 GeV plus or minus some spread. And that spread is the reason that this migration matrix is not just all along the diagonal, okay? And that migration matrix then is what you invert to get this red arrow here, okay? So the migration matrix gets you from particle 4 vectors to the data, and then inverting it is the red arrow that gets you, in the case of the measurement, back to the true particles. I hope that clarifies a little. Great. What I've put, you'll see linked beneath these, beneath the slides, you'll see some questions for discussion this evening, and I want people, just maybe worth, unless there are other questions right now, just saying I'd like bear in mind those discussion questions. I mean, some of the tutors, I'll be wandering around as well. There aren't necessarily right answers, okay, to those. They're the issues that you ought to discuss in different measurements, and I want you to just kind of talk through and think, you know, in what cases might one thing be the right thing to do or another thing. Some of them have clear right answers, but some of them do not. And really there are discussion points about, if you were trying to either use a measurement as a theorist or make a measurement as an experimentalist, how would you address, what kind of things would you have to take into account to address those questions?
Okay, I don't see any other hands or questions. So these are good starting points to discuss in the evening, and maybe you will find some more points for discussion, especially since, as John describes, this is kind of also an art where you don't always have an obvious right answer. Needs quite a bit of thought and discussion how to do this measurement.
Yeah, you always have choices. The really important thing is to decide, is to be clear what choice you made.
Mm-hmm. Yeah. All right, then I think we can close this session, take a break for half an hour. See you back at 11:30 for a talk on electric corrections. Thanks, John, and we'll see you again tomorrow.
Thanks, everyone.
And in the evening.
See you this evening, yeah, actually. Okay, bye.
Cool. Thanks.